Welcome everyone, and thank you for joining this third day of presentations at this workshop. So we have three speakers, three talks in this session, and then a break, and then three more talks. And so my name is Xavier, and I have the pleasure of chairing this first session today. And before we start, just wanted to remind you, as Gemma has done already in the chat, that we are about to record the meeting. So if you do not want to be recorded, you can turn your camera off and use the chat to ask any questions that you want. And so at the end of each talk, we'll have time for questions, so either live or through the chat. And I suggest we start now with the first talk. So Mooly, if you want to share your screen. So the first speaker is Mooly Sagiv from Tel Aviv University. It's a pleasure to see him again. And well, he's well known for his work on the static analysis of programs using abstract interpretation and automated theorem proving. And in particular, well, his work on shape analysis has been absolutely remarkable. And today he's going to talk about blockchains, an area where there's lots of things to statically analyze and verify. Thank you, Mooly.
Thank you, Xavier. I'm really excited and honored to be here. I don't know if it's possible, but if it's possible, I would love for you to ask questions during the talk. Unfortunately, I can't see your text. So if you talk, I will be able to hear you. So I will be talking today about applying formal verification or hostile deductive verification to the domain of smart contracts. And this is actually something that is done now as part of the company that Sherry Grossman and myself established. And it's actually a company which is located in Seattle and Berlin and Tel Aviv. We have quite a sizable group of experts in formal verification and code security. And we are applying technique that all of you know in this domain of smart contract. And I will try to explain to you some of the things that we found during this journey. And we also have academic collaborators. We are collaborating with academic, and this is a work that will appear in CAV. Maybe I will talk a little bit about it, but we are very welcome collaborating with academics on this topic. And maybe I start with some kind of quotes, which is actually interesting how this technology is applied. So we know formal verification has been here for decades, but we think that this is actually a killer application of formal verification. And the reason is that it actually allows you to develop the code faster. And basically what happens is before you deploy the code, you run this formal verification. And one of our clients is Coinbase. Many of you know, but for those who don't know, this is the largest exchanges. So this is like a bank, and what they do, they list tokens of which are developed by other people. So it's basically for third-party software. And what they do, they scan the code with our technology, and in fact, this is actually how it saves them a lot of time, because they, instead of every time when they list new token, they will check it with this technology. The other application of this technology, which is actually something that we always thought about, is that for developers, when you are developing your code, you need to check it. And Aave is one of the protocols. It's a European protocol. Actually, it's a UK-based company, and it's a lovely UK-based company. And what they do in version 1, they use manual auditing, which is a very, very careful procedure that people review the code, they eyeball the code. But with our technology, we were able to show them that even after the review, there is a problem. And in V2, now they can actually we can actually show that there is we can prevent these bugs to occur. So this is something that is a game changer in this development, that you have this technology that you can check the code before it's deployed as a complementary procedure for auditing. So what is a smart contract? So smart contract is, you can think about it like some kind of a logic that there are users who are interacting with money. It need not be money, it can be something else. And there is the code and the storage, and they implement some kind of logic. So here is a very, very simple smart contract. I have this logic that says that if the share of Google will raise to $1 million, I will give some shares from Alice to Bob, and I will pay Alice $1,000. So this is some kind of agreement, and this is usually implemented in code. It's a low-level imperative program that implements them. And you can think of auctions, election, and many other things. And maybe this is something that you are familiar with, but there is actually the killer application of this technology is what's called DeFi, Decentralized Finance Application. So these are code which are implementing economic procedure. For example, lending. You lend some money to some people. Another application is exchange. You exchange money. And what you can see here, and that's actually amazing, you can see how this space is progressing in terms of total value locked. How much US dollars are locked in every contract. This number is actually, we took yesterday. This is a very interesting number. So you see actually that this is like the ride is pretty, it's actually, it's like a roller coaster, a lot of changes. And you see that over here, which is actually our customer, they're actually now number one. And you see how much money is actually, so there are billions of dollars who are actually being deployed in smart contracts. So we think that actually there is a big pain point in terms of bug here. There is a high risk. Every time you execute a transaction, if it's a buggy, unlike the transaction that you do in a normal bank, there is no way to reverse this transaction. And code correctness is really a acute problem. And here we are showing you here only the bugs that happened during 2020. And actually, this is something I took from the website, and you see that $96 million actually were lost because of these bugs. By the way, feel free to ask me questions, but so far it's quiet. Even I lost my chair, I guess. So we think that this is a perfect domain for smart contract because code is law. So if you have a wrong code, you have the wrong law, and the bug have actually a huge impact, and it's hard to mitigate these bugs. And just to show you what we learned during these 2.5 years, so what happened is that we actually came together with our customer with some kind of rules. So for example, one of our early customer is called Compound Finance. In Compound Finance, I cannot see the chat, by the way. If you want to approach me, please. So one of our early customers, they defined the property that any loan could be fully repaid. And that's a logical property that you want to hold. And another customer, which is Coinbase, they require the token supply must be bound. So what we can do, we can run this deductive verification and check these properties. So if, for example, when we run the tool is able to identify an error case. There is an edge case in which you can actually violate this property that any loan can be fully repaid. And when you fix the code, you can show that this is correct. And with Aviv, we can show this violation. With Maker, by the way, Maker is another player, European player in this space, which developed a lending protocol. And Cello is a key player in this place, and so on and so on. And what we think that unlike usually when one of the problems for formal verification is that the code, when you are ready with the code doesn't change a lot. But this is a case where the business actually dictates that the code, when you have V1, you have V2, you have V3. So the business need for this is obvious. It's basically a continuous integration of checking the code. That's how our tool is shaped. So I wanted to make this talk a bit more technical. So I decided to actually take one property, which I think is interesting for our community. And the property is called solvency. I'm sure we all know what it means intuitively. It means something like, even if everybody behaves badly, I can get my money back. So basically, Shankar, if I invested my money, Shankar can never take it from me. And this is a really interesting property, and you can, of course, formulate it. One way to formulate it to say for any deposit, there exists a possible way to withdraw it. So this is a very tricky temporal property. You can define it in branching time temporal logic. Every time you have a deposit, there exists a path in the tree where you can withdraw. So here we are displaying it. You have this op1, there is deposit, and so on. As long as there is deposit, it's okay. But the problem is that sometimes the thief can actually make a place where you have a deposit that no way what you actually will not be able to withdraw. So probably the simplest case that you probably many of us heard about is Ponzi scheme. Okay, so Ponzi scheme is a case that you lead to insolvency. Is this property clear? So this is the property that we claim it's interesting, and it's very hard to monitor it, and it's very hard to verify it. But this is the property that we are interested. Of course, it is in smart currency, but it's a property that you want in a bank account, in options. Maybe you want to refine it. Maybe you want to have something slightly weaker, but let's assume this is the property.
So Mooly?
Yeah.
So wouldn't you want to be able to also say that, I as a user can actually, choose this path? It's not that it's possible, but that, I can actually control it.
Yeah, that's a very good point. So maybe you want even something stronger. You want something like there is a way. You're absolutely right. Maybe you want something stronger. Maybe you want to have something that you say you can control it, and maybe also that you want something weaker because, for example, some of our customers are implementing options. This is too much too hard because maybe the share got down. So in fact, you are right. Shankar is right. It's something you want. Maybe you want something stronger. Maybe you want something weak. So what I wanted to do today is to be able to cover 3 things. And the third one is probably the least important, is what we do as a company. But I want to actually talk first about what are the solvency violations. And actually, these are the things that we are learning in the company, and it's lovely. Actually, we are finding cases that you can have insolvency, and these insolvency are actually, it's once you have them, it's like a disease. The protocol is in some sense dead. So this is what we are finding with formal verification. The way we are finding them at the moment, we are just defining hostile, invariant, or relational property. So we are actually coming back to defining basically whole triples and then using technology that can actually check the bytecode and see that these whole triples either hold, or most of the cases it's interesting when these whole triples are violated. So that's what we do. So I start with a trivial example. It's actually nothing real and nothing, but it probably will get you the idea. Later on, I'll go with more real code. So this is sort of the simplest implementation of a smart contract. I am writing a code in Solidity. It doesn't matter if you don't understand it. I will explain. You have a bank, and every account, every address is mapped to its value. And there is a total value which is intended to cover the total. And then there's a function deposit that deposit the value. So you have an address and you deposit into the address. Assume that you have this value outside the blockchain or maybe in another smart contract. And you have a withdrawal that takes the money from the address. And just to make it a little bit interesting, I wrote a transfer that basically I can transfer from me to Peter. So there is a transfer. And this is a very, very simple, interesting protocol. Trivial. Is it solvent? I guess I'm not allowed to ask questions.
Just a quick question. Should we assume, are these atomic transactions?
Sorry?
Do these transactions execute atomically,
yeah,
or can they interleave?
Daniel, they're atomic. Yeah. One of the beauty of the blockchain, that the blockchain gives you atomicity. The order is not determined, but the blockchain technology, the nice thing about it is give you atomicity. So basically, my deposit and Xavier deposit, they can be, I don't have a way to control their order, although it's between different nodes, there is consensus. But deposit, once it's executed, you can guarantee that it's executed atomically. Okay, does anybody want to guess? Is it solvent or not solvent? Okay.
You look like you're in the territory of the DAO bug, so I'm going to conjecture that that's falls prey to the DAO bug.
So that's
I'm also assuming there's integer overflow here. I don't know what the semantics are on integer overflow, but
yeah, so that's actually interesting. This code, so you're right. So I think Phil is right that the DAO bug is problematic, but actually the DAO bug is not. There are many more bugs beyond the DAO bug. And I think the other person, which I didn't get about overflow, there's no overflow. The code is actually written, the guy who wrote it actually wrote it, so there's no overflow because he's checking the require. This require behaves strange in Solidity, but this thing is implemented in 256. So it means that if you ask if total plus amount is greater or equal to amount, it means the total plus amount is less than 256. So that you are absolutely right. All of these bugs that you are saying, but interestingly, these bugs are not of the. There are many more bugs beyond the DAO bug, and I will show you them here. Okay. So of course you understand. If I ask you, it's not solved. So how is it not solved? So let's see. So let's just look into my transfer function. It looks very natural. I just did this, and you see this code is like code that you see in an undergraduate student. And basically, you see now there's Alice has 40 coins, dollars, and Bob has 20, and the total is 60. And basically, transfer from Alice to Bob. It does what you expect. Basically, Alice now has 2, and Bob has a total. So I'm giving you a little hint. If you are a hacker, and there are many hackers looking into this code. All of this code is, by the way, open source and publicly available. It's a heaven for hackers, and there's a lot of money. So if you're a hacker and you're looking at what you're going to do, so the thing is that the hacker did something like this. He did transfer Alice. And what will this do? Can you tell me what will this do? It's a silly code. I mean, the hacker does it in much more complex things, which I will not be able to explain. But what will this do in this code?
oh, it just overwrites it.
Exactly. So basically, Alice lost her money. That's not so bad, but you know now if she said, but actually this is like there are many like this. So this is just 20 million. Okay. I don't know. I just pasted the tweets. So it's a 20 million bug. I can show you. I will show you more interesting. But that's a $20 million bug. Basically, if you think about it, you are transferring to yourself and you go. So what are we doing as a company? So our policy for that is that we are writing invariants. We are writing the usual invariant that you know. So here are this invariant that you want. Basically, the total is the sum of the balance, and that for all address, basically the balance is equal to the sum of the deposit plus the transfer of the money that got into me, and plus minus the withdrawal of the money that I'm sending and the transfer. And the nice thing about this invariant, they capture many of the solvency errors. So for example, you see in this case, the invariant is maintained. Sorry, in this case, the invariant is broken. So you see that basically, if we knew this invariant, and if this invariant would be enforced, even if it would be enforced at one time, you could perhaps check this transaction. But at the moment, and by the way, it will also avoid the DAO bug and others. But the idea is if the user is willing to write this invariant, then actually we can check this invariant. And we are checking them statically using hostile verification, but maybe even in certain cases, you can check them dynamically. And when you correct the code, of course, you see here is the corrected code, the code which is solvent. So code which is solvent, then now you see that you are doing this total balance. And now if you're doing transfer Alice, it does the right thing. It doesn't change anything. So you see that this is when you have the corrected code satisfies the invariant. Okay? So this is just one case of insolvency. As I said, this is not realistic, but it's actually inspired by a realistic case. What we do in practice, we actually write relational property. So I think this is known in our community that instead of just checking properties of one program, we are comparing several programs. So here you see this is the property of deposit and transfer. And for example, you require the deposit is is additive. So if you do deposit AX and you do deposit AY, it's equivalent in some sense in terms of the state to deposit A of X plus 1. So we are writing these rules, and then these rules are checked by our tool. But the interesting thing is coming up with these rules, coming up with these correctness rules for DeFi.
Mooly, just to remind you that you should stop in a few minutes so that we maybe 3 or 4 minutes so that we can have time for questions.
Oh, I'm only at the beginning. Okay, so I'll wrap up. So you had question during the talk, but never mind. Okay, so I'll do what you do. You are the chair. So the sushi swap is actually another protocol which is tricky. And it's interesting how this domain is going. It's like this is another great team all over the world, actually in Europe, in Australia, in the US, and they basically established this company that does this exchange that I talked to you. But it's a decentralized exchange, which means the exchange is implemented with a code, and it's very tricky code. And you see that even though it's a small company, it already has more than $3 billion of value. And what this code implements, and I will go over it quickly, sorry for that. I don't know how much you can get, but it's in our website. Basically, there is an article about it. And what you see is that basically it's implement a mechanism of liquidate. So if I owe the money too much and the money is covered by, when I take a loan, there is a collateral. And if I cannot pay, then you liquidate my loan, use the collateral. And you see when the liquidate is executed, it does the right thing. The yellow show the system and the green show the user. So in this case, Bob actually covers Alice's loan and everything is good. But you know this we know as programmer, when you have execute, when you have the ability of somebody to execute code of behalf of somebody else, then here is another case that you can prevent solvency. So you see that here Mallory, actually, instead of covering the loan, Mallory is executing a code with the message sender being herself. So what happened now, the system pays itself. Once the system pays itself, you see that the loan is actually covered and the collateral is reduced. So it's another case of solvency. So this is a very tricky case of solvency. And when we show this to the team, actually, they love this technology. So this is actually totally amazing how you can find these kind of things. And they work with us. It's very nice for them because they can develop this sophisticated code, and then formal verification can actually find these bugs or prove their absence. And the property that we check is anti-monotonicity. Basically, we check that if the borrow is increased, then the collateral is decreased. So the anti-monotonicity between the borrow and the collateral. And just the last one, this is Balancer. So Balancer is another beautiful protocol. It's exchange protocol. They are moving now from V1 to V2. It's actually very recent. And basically what happened here, it's a case that you have collected fees and user balances. And because of there is a mistake here, another additivity error, actually the case that you have insolvency. And it's a case, and I should say, this code was carefully audited and still formal verification can detect this error. And what's the property that we check? By the way, I should have explained what is flash loan because many of you don't know, and I didn't know before that, but flash loan is the ability to take a loan and without collateral. And the idea is you take a loan and you return the loan at the same transaction. So it's okay, and actually it's used in this thing. So what we check here is again that the flash loan is additive. If you take two loans, it's like taking each of the loan and then taking their sum. And it's again, it's finding these corner cases. So I'm almost out of time, I guess. Tell me. So what we did, we implement that. So basically, we take the code. And the code is written at the bytecode level. We take the code at the bytecode. We don't take the code at the source code. We write the specification, the whole style specification outside the code, because we want to make sure that when the code is changed, actually the specification remains the same. And then we have this prover, which is actually implemented, and it either can give you a guarantee of this environment or can give you a test case. And when you change the code, the idea is that during the CI, you check that these rules remain correct. And how is this implemented? So basically, there is a decompiler. If you know tools like Suit, it takes the code and actually there is a static analysis. It recovers the high-level location. Then there are these rules, and you generate an SMT formula, which is fed to SMT solvers like Z3, CVC4, Yikes, and others. And there are a lot of challenges in terms of SMT, but I'm not going to be able to talk to you about. I won't talk to you about decidable logic, but I will just say that we have many invariant, and we can tell you all of them. And just to what you can take from here. So DeFi, I think it's an interesting domain for formal reasoning because you can change the paradigm from code is law to spec is law. And we think that solvency is an interesting property, although there are of course many others, but each DeFi has its own invariant for solvency, and we use SMT and static analysis for checking the solvency. Thank you, Xavier, and sorry if I ran over time.
Well, thanks a lot, Mooly, and you can catch your breath now. Okay, so yeah, we have like, let's take 5 or 6 minutes for questions. So you can either ask questions in the chat or just speak. And oh, someone raised their hands. Danielle, if you want to go first.
Yeah, so I'm curious about sort of what features of the Solidity language either lent themselves to formal verification or made formal verification difficult. And if you were writing a language for an application like this, what would you do differently?
Yes, so we don't handle the Solidity itself. We use a Solidity compiler to map into bytecode. And one of the interesting things that happened during this process, and you can read in our website, we find many compiler bugs. So actually we have something for, so maybe Xavier wants to see, because we are finding a lot of interesting bugs in the compiler itself. But we are
Good
handling, sorry?
Good to know, thank you.
Yeah, we are finding many bugs. Some of them are mind-blowing, like memory things. You can read them and they're actually acknowledged by the Solidity team, who's usually fixing them quite quickly. This is a domain, by the way, also our users, they are very receptive for bugs. So we are not handling Solidity, but I can tell you that there are a lot of things that are interesting in this domain from a reasoning perspective. Is that what you are asking?
Yeah.
So think about something like, I don't know if you know, like economic things like this Scholz procedure, nonlinear arithmetic, maps. There are a lot of things in terms of the domain. The domain is wonderful for, even there are some linked lists, but not so much. But there are a lot of things here. There are some. So in terms of if you're asking for reasoning, it's a very challenging domain. It's a small code, but it's a small tricky code. The thing which is nice is that, and this is somewhat modular in the sense that one code, when one contract is calling another contract, usually you cannot assume anything. So that makes verification a bit easier because there's a little less code to analyze. Although some of our code we have to analyze several contracts together.
Okay, so there's one question in the chat from Sanjiva Parzan. So he asks, what is the logic in which you write the spec? So if the spec is the law, what is the logic in which the law is written?
Yeah, that's a very good question. So we keep changing it. We have a domain-specific language, which is I guess we are trying to make it like Solidity, but we are adding a lot of things for math. Like we have mathematical integers. We have the ability to record the state, so you can check relational property. You can say something at this state and something at that state. So we are adding things that, of course, are not executable and quantifiers. We are adding things that are demanded by the user. Now we have ghost in the language because you have something, especially because we are reasoning at the low level. You want to reason about something which is changed. So we added ghost in our language. Our language is open, by the way. The tool is not yet open, but the language is completely open because that's what we want people to use.
Okay, so Philip Medler has a nice question. Philip, do you want to ask it live?
Sure.
Thanks.
So, hi, Mooly. So congratulations on having an example other than the DAO bug. As you'll probably know, right, there's zillions of papers saying we can find the DAO bug, and then you read the paper, and it turns out they already knew about the DAO bug, and so they go looking for it. But you are doing the right thing. You've got an invariant that would let you find the DAO bug even if you didn't know about it. And you've got these other interesting invariants as well. So I think having those invariants is really quite valuable. Have you published them anywhere? Is there a repository of these invariants or technical papers describing the sets of invariants that you use?
So unfortunately, the only publication that we have now, I know it's terrible, is GitHub. So we basically, we are a company and we are sweaty, we should do it, you are right. But we have actually, there was a year ago, 2 years ago, there was a Stanford blockchain conference, and there we published because Dan Bonnet asked us and we did that, but we need to do it. But at the moment they are published, they are published, but they are written in our language. If you are fine reading our language, then the answer is yes. But maybe you want something like more academic article. That's what you want, I guess.
I want something I can read. Academic articles are an example of that. Yes, I encourage you to publish. I'm actually working for a different blockchain firm, IOHK, and one of the unique things they do that's not just unique among blockchain firms, it just seems unique among industry, is they actually care about peer review. They want everything they do to be peer reviewed. I think that's such a wonderful standard. I encourage your company to adopt that as well.
So we do that, by the way, we do that. We do that. We have actually, I don't know if you know, many of our students are graduate of university, PhD from University of Washington, from Freiburg. They review carefully, actually. They are very good reviewers. It's just that we are reviewing that at the GitHub level. We are reviewing every rule because, and actually, you know who are our best reviewers? The developers. Because if you write the wrong
review
rule,
is really important also.
Software. Excuse me, gentlemen, we still have a couple of questions on, so maybe Peter Müller, maybe.
Yeah, thank you. Thanks, Mooly, for a very nice talk. I was wondering who's writing the invariants? Are these the verification specialists from your team, from your company, or are the developers able to write their own invariants?
That's a great question. So the answer is probably a mix. We would love to be only the developer, but some of the cases it's us, some of the cases we start, they continue. It depends on the team and us. So we don't want to be a professional service company, so we much rather them write the invariant. But it's a tricky thing, and we need to teach them. So I don't know if you see in our website, there are a lot of lectures by James Wilcox, by myself, about how to write invariant. We are trying to teach them how to think in these cases and how to think, so that, because when they write this language, they say, what is this language and how is it that I don't have concrete value? So we are trying to teach them. Ideally, we want them to teach. We want to create a community of users, and if you know people to help us, it's great. And we can, there's no absence of money in this space. So if somebody wants to know math and wants to write specs, there's a lot of value here. Even part-time writing specs is good.
Sounds good.
And one thing that I didn't mention in the talk, which is pretty interesting, is that there is a network effect. The specification that you write for one protocol, you can actually use it in another protocol. So it's hard to write the spec, but you can reuse them.
Thank you.
Okay, well, thank you very much. Thanks again, Mooly, for that talk. Supratik, if you're ready, you can start sharing your screen.
Can you hear me?
Yep, we can see you. And here are your slides. Excellent. All right, so the next speaker today is Supratik Chakraborty, who's from Indian Institute of Technology in Mumbai, where he's been working on a number of topics in theoretical computer science, but that also includes formal verification by static analysis and model checking. And today we'll talk about a new technique for verifying array programs, and that sounds extremely interesting. Thank you, Supratik.
Thanks, Xavier, for the nice introduction. And hello, everybody, in whichever time zone you are. So I'm going to talk about a technique called full program induction, which is we have been using for verifying programs that manipulate arrays. And this is joint work with my PhD student, VSOW04, who is in the audience, and my colleague, Ashutosh Gupta. Okay, so here is an example of a program which does some, updates and reads on an array A. And this array A is of a parametric size n. I have highlighted n in red. And the parameter n is actually used in the program in multiple ways. For example, it's used in loop bounds. It's used in loop bounds. It's also used in branch conditions, and it can also be used as a data value that is used to compute expressions that are assigned to other variables. So we will call such a program P, which has a symbolic parameter n as P sub n. And of course, given such a program, we can also have a precondition and a postcondition, which are also parameterized by n. So in this particular case, I might say that we start off with all elements of the array A being initialized to n, where n is the size of the array. And then the postcondition might require that after this program terminates, every element of the array has the value n times n plus 5 over 2. So the generic idea is that we have a parametric Ho triple where the parameter is n, and I'm going to, in this entire talk, I'm going to pretend as if there is just one parameter n, which denotes the sizes of all arrays. But in our work, we can actually deal with multiple parameters as well. But for simplicity, I just keep it to one parameter. So we are required to prove that phi n, p n, psi n holds for all n greater than 0. Okay. And the technique that we're going to use, which we call full program induction, is to basically induct on the entire program Pn instead of inducting on individual loops and sequences of loops and nested loops and all of that. So here is what we are trying to prove, that phi n, p n, psi n holds. So we will say, okay, let's make sure that the base case holds. So does phi 1, p1, psi 1 hold? And if it does, then I'm going to make an induction hypothesis that phi n minus 1, p n minus 1, psi n minus 1 hold. And I'm going to talk, in much more detail about what p n minus 1 means. But phi n minus 1, psi n minus 1 are just saying, take the formula phi or psi and replace the parameter n with n minus 1. So that's going to be my induction hypothesis. And then my induction goal is to prove phi n, p n, psi n using this induction hypothesis phi n minus 1, p n minus 1, psi n minus 1. And notice that in all of this description, I'm treating the entire program, the full program, as one block. So the basic idea that we're going to use is we'll say that, okay, we will try to express the program Pn as Pn minus 1 sequentially composed with something that we call a difference program. It's delta Pn. And here we have our induction hypothesis, phi n minus 1, p n minus 1, psi n minus 1. And we're going to ask, well, what if I were to get phi n starting from phi n minus 1? So maybe there's a, an additional part here, which I'll call delta phi n. This is kind of the, the incremental part of the precondition. And as long as this incremental part of the precondition is not affected by this program p n minus 1, as long as it's not changed, this is going to come as is over here. I mean, once again, in our actual work, we do allow this to be modified in certain ways, but just to keep things simple, I'll say that this comes down straight as is. And then, our goal is now to really prove this last part, right? Because the phi n minus 1, p n minus 1, psi n minus 1 already follows from the induction hypothesis. So our inductive step is really to say, take psi n minus 1, take delta phi n, combine them in whatever ways are appropriate, and then try to prove this Ho triple. And note that this Ho triple is trying to reason about the difference program, delta Pn, and it's also using this difference precondition, delta phi n. So, when we try to do this, sometimes it so happens that just starting from psi n minus 1 delta phi n, we are unable to prove the postcondition psi n. So we try to find, okay, what would be a weakest precondition for this, if this can be calculated. And I'm going to show you cases where it's difficult to calculate and what we do in those cases. And so we calculate a precondition, p n minus 1, and we strengthen the precondition with that. but simultaneously we also strengthen the post condition, because remember, this is an inductive proof. So if I prove something holds at the end of the n-1th step, I should also try to prove that it holds at the end of the nth step. And we continue this process, trying to find out pre-n-1 and pre-n. And this process terminates. If we reach a fixed point, then we have been able to prove the program inductively for all possible n. Okay, so there are some niceties about this technique. So first of all, if the difference program is loop-free, then it does seem to simplify verification. And it turns out that for certain classes of programs, indeed computing this difference program is loop-free. And here I've listed a few cases, like if there are simple cases, if no data dependence across loops or loop iterations, if the individual elements being updated are not affected by the value of n, and so on. In our paper, we show that delta Pn can be computed in other cases too. But of course, there are problems, and the rest of the talk is really about trying to address those problems. Note that computing Pn-1 and Psi-n-1 are really trivial. It's just saying replace the parameter n with n-1, and Psi-n-1 is directly useful during the inductive step. Okay, so let's now focus on this, that computing delta Pn in some simple classes of programs, it might be easy, but in other classes of programs, it might be difficult. And what do we do about this? Okay, so just to illustrate the kind of difficulties that arise, I've taken a simple example here. So this is an example with two sequentially composed loops. And as you can see, the parameter n is used as a loop bound and also used as a data value to update elements. And here I'm updating a scalar, and I'm also updating arrays over here. And this scalar, which is updated here, and it's kind of iteratively updated within this loop, is then finally used in the second loop. So there are all kinds of dependencies within a loop, across iterations of a loop, and also from one loop to the next. And if I were to try to apply this full program induction technique to this, my Pn-1 would look something like this. Basically, it's the same program Pn, but I have replaced every occurrence of n with n-1. And then if I were to sort of find what is the difference program delta Pn, such that Pn-1 composed with delta Pn is semantically equivalent to Pn, now this program turns out to be fairly complicated. As you can see that I actually have to bring back both these loops here, and within those loops, I have to kind of do some repair because here I was updating with n-1 whole squared. I should have updated with n squared. So I have to do some repair here. And then, of course, this loop was iterating n-1 times, so it missed one iteration from Pn. So I have to put that missed iteration back here. And then again, I have to compensate for whatever damage was done, because x here should have taken the final value as it comes out of this loop in Pn. But here, the x that was used took the final value coming out of this loop in Pn-1. So, this is a pretty horrible looking delta Pn. And that's the point that I want to emphasize, that constructing delta Pn can get non-trivial. And in this particular case, for example, delta Pn itself has two sequentially composed loops. And so analyzing it might be as hard as analyzing Pn itself. And in fact, to analyze delta Pn, I might have to recursively apply full program induction on it. So while the idea looks appealing, that to induct on the whole program, there are challenges. And what I'm going to do is to try to describe how we go about addressing these challenges. Okay, so in addition to what I just showed you, there are additional difficulties with full program induction. For example, if I have a branch condition that depends on n in Pn, then in Pn-1 that becomes n-1. And now, if I'm trying to say, okay, what should I sequentially compose with this such that it sort of has the effect of this, that's kind of non-trivial, because I have, if n is even, then n-1 is odd. So obviously the opposite branches have been taken, and so on and so forth. Similarly, if I have nested loops, there are problems again, because the inner loop here itself has already missed some iterations. And so not everything is rosy really with full program induction. So the idea of inducting with the full program sounded interesting because it allows us to use an induction hypothesis, which is already talking about a program with perhaps nested and sequentially composed loops. But generating delta Pn can get really difficult. And so, we ask, can we somehow reduce the difficulty of generating delta Pn? And of course, there are no free lunches here. So there is a trade-off, and this trade-off is how easy is it going to be generate the difference code versus how easy is it going to be to use the induction hypothesis. And what I'm going to talk in the remaining time is is the technique which shows that perhaps the ease of generating the difference code wins, because you need to sacrifice a little bit about how to use the induction hypothesis, but not much, but you can really simplify how to generate the difference code. Okay, so here is what we're going to try to do. So this is the existing, this is the full program induction strategy that I just talked about. We're going to try to say that, okay, maybe we don't need to keep Pn-1 as is. We can take a very carefully controlled modified version of it called Qn-1, and similarly a very carefully controlled modified version of Phi-1 called Phi'(n-1), and similarly for this difference. But we're going to ensure that the difference program really is the peel of this program. What do I mean by peel of Pn? It just means peel off the nth iteration of all the loops, of all the nested loops, and just put it down over here. And this is how I'm going to construct the difference program. And the idea is, can we make this work? So this would really simplify generating the difference program. But of course, now I can't use the inductive hypothesis straight away. So I have to do some additional jugglery to be able to talk about this Qn-1, Phi'(n-1), Psi'(n-1). And so we're going to try to see how to go from the left side to the right side. Okay, so here is what we want to do. And as I just said, peel of Pn is just that. We just peel all the loops, and I'm going to show you how we do that. Qn-1 differs from Pn-1, and we will once again see how to do that. But this difference is only going to be in the loop bounds, which means that a loop that was iterating n times will now iterate n-1 times, or whatever function of n times will now iterate function of n-1 times. But in all other places, for example, in a branch condition or in an assignment statement, if the symbolic parameter n was being used in Pn, it will continue to be used in Qn-1. So Qn-1 does not change the way in which n is used except for loop bounds. And as I said, delta Phi'(n-1) and delta Phi'(n-1) are kind of similar to Phi'(n-1) and delta Phi'(n), but minor differences. And the Psi'(n-1) is probably not going to be the same as Psi'(n-1) because I have a different program, a different precondition, but this is going to be closely related to Psi'(n-1). And this close relation is going to be through what we call differences or difference in variance between Pn-1, Qn-1, and I'm going to elaborate on this. So what we really want to ensure is that we get a Phi'(n-1, Psi'(n-1), and Qn-1, such that if the inductive hypothesis held, then this whole triple would also hold. And if this whole triple holds, then we can now proceed with our inductive step here using just the peel of Pn as the difference program. Okay, so let's see how this works out for this example. So this was our earlier example, and we knew that if I try to complete the difference program, things were not very pretty. So here is how the new strategy allows us to compute the new difference program, which is just the peel of the first loop, the nth iteration of the first loop, and the nth iteration of the second loop. And here is Qn-1. And if you look at Qn-1 and Pn, the only difference you'll see is that in the loop bounds I have used n-1 and nowhere else. And notice that this is different from Pn-1 because in Pn-1, every place where n appears gets replaced by n-1. So even here it gets replaced by n-1, here it does not. But of course, this means that Pn-1 and Qn-1 are not the same programs. They're closely related, but they're not the same. And so the post conditions will be different. Okay, now how do I get this Qn-1? So basically what I do is, and this is just to illustrate through a simple example, I peel off the last iteration of this loop, and then I see wherever this is being used in subsequent iterations, and I just do that substitution straight away. So for example, instead of x, I will say x plus n times n. And then after I have done that substitution, I can just move the peel down over the body of the next loop, and that's what I get there. Okay, so this can be nicely written down as an algorithm. And here is another example. For example, in this example, I'm X is getting incremented by 5 in each iteration. So I peel it off, take off the last iteration, and then I see wherever next it is being used in subsequent loops, I go and replace X with X plus 5 over there, and then I can move this peel over the body of the next loop to generate the reference program. Okay, now here is a simple example of how we deal with nested loops. It turns out that even nested loops can be handled, modulo certain restrictions with this technique. So for example, here is a simple loop, and this is just one kind of nested loop. I mean, there are other kinds of nested loops we can handle. For example, the outer loop is going from 0 to n minus 1. The inner loop is going from 0 to I minus 1. So conceptually, what we are doing is we are sort of viewing this nested loop as one loop in which this inner part, the inner loop, has been sort of unrolled into I iterations. Conceptually, this is what it is. And then we say, okay, now I want to peel this outer loop. So if I peel this outer loop, what happens? The last iteration of it, this rectangle box with sharp corners, this comes out. And this part, which is really the inner loop executing in the ith iteration, the last iteration, this comes out as n minus 1. And so now we have our qn minus 1, which looks like this. It's only the loop bound that has changed. And the peel now looks like this, which has this big rectangle over here. And these things, which are, n minus 1 copies, is just this this inner loop brought out here for the last iteration of the outer loop. So interestingly, note that the peel of a doubly nested loop is actually a singly nested loop. And it turns out that this can be generalized, and we can show that every time we peel in this manner, under the restrictions that we require, every time you peel, the nesting level of the loop is going to reduce. And so it is not surprising that earlier when we took, in this case, when there was no nesting, the peel is actually loop free. Okay, so this allows us to deal with certain classes of nested loops as well. And then there are some syntactic restrictions on the program. So basically, we have a grammar. What it does is it disallows unstructured jumps. Within the loop body, we disallow updating the loop counter. The upper bound expressions are, of a nested loop is only in terms of n and the outer loop counters. And the nested loop, if at all, is the last loop. I mean, we can have sequentially composed loops, but if there's a nested loop, we require it to be the last loop in the sequence. Now, these restrictions, once again, simplify things. There are relaxations of these restrictions also that we have worked out. But, once again, for the purpose of simplicity, we'll just go ahead with these restrictions. And then we have some, guarantees that we can provide that the sequential composition of Qn minus 1 and peel of Pn, which is generated by our algorithm, can be shown to be semantically equivalent to Pn. And if Pn satisfies our syntactic restrictions and the upper bound expressions of all loops are linear expressions in n and the loop counters of the loops that nest it, then we can show that the maximum nesting depth of loops in peel Pn is strictly less than that in Pn. And this is kind of the progress guarantee. So if I recursively apply it to peel Pn, I know eventually I'll end up with a loop-free difference program on which I can perhaps use a bounded model checker itself to check the property. Okay, so the part that still remains is how do I compute the psi prime n minus 1 from psi n minus 1? And the way we do this is we look at these two programs, which, as I said, are closely related, and we infer relations between the variables in this and the variables in this. And this is somewhat similar to what happens in translation validation, where you have two slightly different versions of the program, and you try to infer relations between variables in them. So we call these difference invariants between the variables in Qn minus 1 and Pn minus 1. And once we have obtained the difference invariants, so we don't really require invariance of the original program, but we require difference invariance between these two versions of the program. Then once we have the difference invariance, we can get psi prime n minus 1 from psi n minus 1 through this simple process. And our observation from our experiments was that finding sufficient difference invariance is often much, much simpler than generating invariance to prove the post-condition directly. So difference invariants are, something is saying that this is that plus 1 in each iteration of the loop, or this is that plus n in each iteration of the loop, things like this. So effectively, we use a guess and check paradigm to guess difference invariance using simple templates. For example, a version of the variable in Qn-1 is the version of the variable in Pn-1, plus maybe some constant or linear or a quadratic function. In all our experiments, we didn't need to go beyond quadratic. Similarly, an array element in Pn-1 is related to the same array element in Qn-1, maybe with some simple function. And finding these functions using these templates turned out to be much simpler than generating the invariance to prove the post condition directly. So here's the big picture overall, which is that we had this as our original idea of trying to induct over the whole program, but this really messes up this difference program generation for a large class of programs, and we can simplify it by really simplifying the difference program, but then we can't use the inductive hypothesis straight away. We need to find this difference invariance and find this new post condition based on that, from which we can complete the inductive step. And the really important finding from our experiments was that finding these difference invariants are much simpler than the real invariants that you need to prove the program. Okay, so
Supratik, excuse me, you should plan to stop in a couple of minutes so that
yes,
time for questions. Thank you.
Sure. So this is the strategy now. We are using the difference program for the peel and psi prime n minus 1 and delta phi prime n. And just like earlier, it is possible that I need to strengthen the precondition and then also the post condition. And this precondition and post condition are not necessarily the same here because there's a transformation that has happened. This is not Pn minus 1 anymore, but then they can be related using some simple relation. And in particular, if the difference invariants are equalities, if something is equal to this plus something or this times something, then computing psi n from psi prime n minus 1 is pretty simple. So here's the soundness guarantee. This is just like any other inductive proof that if the whole triple holds with the post condition strengthened up to a certain natural number, and then this is the relation that I just talked about between the thing that we strengthen the post condition with and the difference invariance, implying the version of it that's to be used in the Qn minus 1, then we can say that if I can prove this on the peel Pn, so this is basically the strengthened precondition along with the inductive post condition, and this is the strengthened post condition. So this holds for all n greater than 0. So this is the inductive.
Okay, I'm no longer hearing Supratik. Am I the only one? Or?
I'm ready.
Okay. All right. So, and yeah, it's about well, the timing is about right anyway. So let's move on to the third talk. So it's given by Peter Müller, who's from ETH Zurich. Well, he doesn't need much of an introduction. In his work on program proof is well known at ETH and earlier at Microsoft, and in particular for verification of object-oriented programs, concurrent programs, and so on. And to my great pleasure, he's going to talk about the Rust programming language and what can be done about it. And to my pleasure, because I find Rust as a very interesting design, perhaps the most interesting new programming language in the last 20 years or something like that. So I'm really happy to hear more about Rust and deductive verification. Thank you, Peter.
Well, thank you very much for a very nice introduction, and thanks also for inviting me and giving me a chance to present my work. So I'm going to talk about a verification project where we are working on a deductive modular verification tool for Rust called Prusty. And this is joint work with several people in my group at ETH and with Alex Summers from UBC in Vancouver. So let me motivate the work by briefly introducing you to some of the challenges that we typically face in the verification of imperative programs in traditional languages like C or Java or any language of that flavor. So this little example illustrates those challenges. So we have a client function here, which takes two integer list pointers A and B. We store the length of the B list in a local variable. Then we append a value to the A list, and then we would like to prove that the length of the B list hasn't changed. And so this assertion basically expresses an aspect of the functional behavior that we are often interested in verifying. However, if you want to reason about such a property, like for instance, if you want to prove that this assertion never fails, then existing verification techniques really force us to consider various other properties first before we can actually get to this functional property. So for instance, we need to prove memory errors are not present in our program. Like one potential memory error in this program would be for the B pointer to be null or to point to an unallocated or already freed portion of the memory and so on. So that's usually a prerequisite for reasoning about functional properties. A second property that is almost always needed in order to reason about functional properties is information about aliasing. So for instance, the assertion in this program only holds if A and B are not aliased, meaning that it's not only the case that A and B must point to different nodes, moreover, the entire lists have to be disjoint, right? Even if they shared a common tail, then the assertion wouldn't hold. So aliasing is strictly necessary for something that we call framing, namely to prove that certain updates of the heap do not affect certain properties about other parts of the heap. And finally, if this whole program is part of a, this whole function is part of a program that might execute concurrently, then you also need to reason about data races and thread interference. And so all of these things really complicate the proof and make things much harder and much more cumbersome. So the last 20, 25 years of research have seen tremendous progress in how we can address those challenges. And various techniques were invented. One of the more prominent ones, for instance, is separation logic. So if you were to reason about such a program in separation logic, you would structure your arguments by having a precise strategy how you reason about the heap memory. So you would, for instance, use assertions that express ownership of a part of the memory. So this points to assertion that I have here in separation logic expresses that, first of all, b.len is a valid allocated memory location. And moreover, it gives me the permission to access this kind of memory. And that implies that no other thread can have the permission. So it's also useful to prove the absence of data races. So now if you want to preserve information hiding, or if you have an unbounded data structure, like in my list example here, then you typically need to abstract those permission expressions to predicates, typically recursive predicates. Like for instance, we could declare a list predicate that in a sense includes the access permissions, the ownership of all the memory locations that belong to the list. Now, once I have such a predicate, I could have one instance of it for my parameter B and another instance for my parameter A. And then techniques like separation logic give me a special connective, the so-called separating conjunction, which expresses that those memory regions that are described by list of A and list of B are actually disjoint. And that means in particular that modifying one of the lists will not affect properties of the other. And now with these ingredients, you are equipped to do a paper and pencil proof of such an example. But if you want to automate proofs, you need even more, because at least SMT-based automation typically requires you to manage very carefully how you handle recursive predicates, because you want to prevent the SMT solver from unrolling recursive predicates indefinitely. So you typically need some kinds of auxiliary annotations that tell the verifier when to go from a predicate to its definition and when to go from a definition back to the predicate. And so you end up with all these complications in your proof. And if you look at like a full-blown example, and here I have one in a tiny font on my screen here, then these ingredients are really all over the place. So I highlighted here with lots of yellow bubbles where in this program I use predicates, I use ownership information, I use disjointness information, and so on. And now this really shows a key part of why reasoning about imperative programs is so hard. So first of all, you really require an expert to write all of these annotations because it requires a fairly deep understanding of the underlying program logic. In my example here, separation logic, but it's actually quite the same for other kinds of program logics to write those annotations. And moreover, all of these steps are mandatory. So you cannot easily skip them because those annotations are not only needed to prove memory safety, they are also the basis of verifying functional correctness. As I mentioned earlier, for instance, aliasing information is really crucial for framing, and framing is needed to prove functional correctness. So all these stepping stones, in a sense, contribute to the inertia that maybe you're just interested in whether certain assertions hold, yes or no. But in order to get there, you have to write all those boilerplate annotations in order to conclude or to provide what we call this core proof. So the core proof is, in a sense, the proof of memory safety, but also the foundation of proving more elaborate properties like functional correctness. So now this pretty much summarizes the state of the art in deductive modular heap-based verification. I use separation logic here to illustrate my points, but it would be very, very similar if you use, for instance, dynamic frames or other kinds of methodologies. So now let's contrast that with a development in Rust. So here I have the same example in Rust, and let's assume that we are ultimately interested in the same kinds of properties, in particular, the same assertion that we want to hold in the end. And now what Rust brings to the table is a very strong type system that helps us establishing these properties. So as you can see in my signature here, in Rust, I would declare the arguments A and B to be mutable references. So this ampersand mute expresses that these are mutable references to lists. And now the Rust type system uses this information to provide a number of strong guarantees. So one guarantee is that the type system ensures memory safety. So it's not possible to dereference null pointers or to have like double free errors or dangling pointers. So nothing like that is permitted by the type system. Moreover, the types give us fairly precise aliasing information. In particular, Rust prevents two mutable references from pointing to the same memory region. So that in this example tells us that A and B must be disjoint lists. If I had shared, so read-only references to the lists, aliasing would be possible, but with mutable references, it's prevented by the type system. So you get a very controlled form of aliasing that is very useful as a basis for verification. And finally, the Rust type system prevents data races by construction, so you know that you have only very restricted forms of thread interference. In particular, there are no data races. And now an obvious question to ask is, well, now with all these strong guarantees that you already get from Rust and its type system, can we use those guarantees? Can we exploit them to simplify verification? And so in the rest of the talk, I would like to show you how we do this in this Prousty verifier. And I'm going to give you an overview of the tool and the approach, and also dive a bit deeper into one of the technical challenges that we had to solve there. So the tool that we developed is this Prousty tool. Prousty takes as input a Rust program, and programmers may, but are not forced to, annotate this Rust program with additional specifications to express functional correctness properties they're interested in. So these might be assertions or pre and post conditions of Rust functions, for instance. And so what Prousty does with this input is it generates the core proof in a variation of separation logic and expresses that proof in the Viper programming language. So Viper is a verification system, pretty much like Boogie or Y3, that lets you express verification problems and provides automated verifiers to solve them. And in difference to Boogie or Y3, Viper really focuses on separation logic style reasoning, so it's particularly well suited for heap manipulating programs and concurrent programs. So what Prousty does is it generates this entire core proof that I've illustrated with all these yellow bubbles on a previous slide fully automatically, and uses then Viper to check that this is actually a valid proof. And if it finds any errors, then those errors are translated back to the level of Rust and reported to the Rust programmer. So let me show you how we can achieve this step by step. So in order to generate this core proof for a given Rust program, we take the Rust type declarations, in particular structs, but also type declarations of other forms. And out of those, we generate fully automatically, without any user input, all the separation logic predicates that we need to describe instances of those data structures. Moreover, we take the signatures of functions, so the parameters and result types, and from those we can automatically synthesize the pre and post conditions that we need for this core proof. Okay, so that's another step that is fully automated. Moreover, we take information that we extract from internal compiler analysis, like for instance, this Rust borrow checker. And out of those, we can synthesize all the auxiliary annotations we need for Viper to check that the core proof is actually a valid proof. Like for instance, earlier I mentioned this process of going back and forth between the definition of a predicate and the predicate itself. So all of those annotations can be extracted from information that the compiler has anyway as part of its type and borrow checking process. And now finally, if the user provides additional specifications, then we use those and layer those on top of the core proof, and we can prove those fairly easily. So therefore, if we apply those steps, we get a solution that we claim is actually usable by Rust programmers for two main reasons. One reason is that the annotation overhead is substantially smaller than what you would find if you just applied logics like separation logic directly. And the second reason is that programmers can now interact with the system entirely on the level of Rust. So they do not have to understand separation logic. All the interactions in terms of specifications, but also error reporting, are entirely on the abstraction level of the source language, which reduces the intellectual overhead dramatically. So let me show you what this looks like. So if I go back to this scenario with the core proofs and all this overhead that we had there, then what we achieve with Brusty is that really all the predicates and all the annotations are generated automatically. So that's why these bubbles are green now, so programmers do not have to write them. Users can write functional specifications if they're interested, and that is happening in terms of Rust expressions, and overall the abstraction level stays on the Rust level. There are no leaky abstractions that would somehow reveal the underlying separation logic to the programmers. So how do we do that in more detail? So let me walk you quickly through the overall approach. Of course, there are lots of tricky details to fix in such a situation, but the purpose of this talk is just to give you a high-level idea of how this generation actually works. So here in gray, you see a struct declaration in Rust for a list of integers. So the i32 val here is the payload, and then you have a reference to the next list node. So this option box is needed, option to terminate the list, and the box to make sure that these are actually references pointing from one node to the other. So therefore, what we get in terms of a predicate is we will, for this list declaration, synthesize a list predicate, which is parameterized by the instance of the list itself, called self. So here on the right, in green, you see the resulting Viper code. And now, since this list struct contains two fields, val and next, we need to reflect those in the predicate. So the way we do this in Viper is we include permissions here. So this is pretty much the same as a points to assertion and separation logic, saying that whenever you have an instance of the list predicate, you own the memory locations for the val and for the next fields. And now, of course, those are memory locations themselves that we might want to constrain information about them. Val is an i32, and next is this option box list. So we will, just like we show it here for the list, synthesize predicates for those, and then include those in the list predicate. So we get an i32 predicate for self.val. So that could, for instance, include the value ranges that an i32 could have. And we can have an option box list for self.next. And so that includes the information that if the option is actually a sum option, not a none option, then you get a recursive instance of the list predicate, which allows you to step through the list step by step. So this is how we get the predicate declarations in the first place. And now we use the function signature, like here my ampersand mute list types, to synthesize the pre and post conditions. So what this really means is that A and B are both lists, and the Rust type system guarantees that they operate on disjoint parts of the memory. So we get a fairly straightforward encoding into Viper. So for our client function on the Viper level, we get a precondition that we need A to be a list and B to be a list, and the two are connected by separating conjunctions, so they are disjoint, and we get the same back for the result. And now the beauty of the core proof really is that once we have this ownership or permission information, it is actually very easy to layer functional properties on top. So if the programmer provides functional annotations, we can just conjoin them to those pre and post conditions. So for instance, the programmer might specify on the Rust level that A is sorted both in the pre-state and in the post-state of the function. And that means we can simply conjoin that to our specifications. That is not possible in standard separation logic, but the variation that Viper supports is called implicit dynamic frames. And implicit dynamic frames allows you to have such functional specs in pre and post conditions. All right. And so now, so that's the core idea. And now I would like to go into a slightly more tricky aspect to show you how we handle that. So one of the more challenging aspects of Rust is so-called reborrowing. So reborrowing occurs when a function takes a reference to a data structure and it returns a part of it. So that happens often in getter operations. Like here I have a function that returns the suffix of a list starting at node number n. Okay, so conceptually what's happening here is you pass the entire list structure visualized here by this blue triangle into the function. And what you get back as a result is a portion of it. Okay, so that means from a Rust perspective, you have a list here with a piece missing, with a hole inside, and you get the whole back as a separate data structure. So now if you look at this function from a caller's perspective, what this really means in Rust is that this list with a hole in it is frozen, it's completely inaccessible. You cannot call functions on it, you cannot read fields of the struct, so you cannot use this data structure as long as it's in this incomplete form. On the other hand, the result, the little triangle, that's a regular data structure. It's fully mutable, you can read it, you can update it. And now the Rust type system will track how long references to this green triangle are alive. And when the reference goes out of scope or gets reassigned, then what's going to happen is that the triangle is fit back into the overall data structure, which is now a complete structure again and becomes mutable again. And now the reason why this is challenging is that we need both a way of describing the permissions to this data structure with a hole in it, because we somehow need to describe the ownership information in our core proof. And moreover, we don't want to do that by somehow talking about the path that you would take to this hole, because describing this path could be very complicated and would definitely reveal implementation details by talking about the fields of the data structure. So we need a more abstract way of doing that. And the second challenge is we would like to describe what the overall data structure will look like when it becomes complete again. And that is challenging because this from nth method might modify the blue part before actually returning. It might also modify the green part before returning. And the caller could make further modifications to the green part, not to the blue part because that is frozen, but to the green part. So actually figuring out what the overall data structure will look like when it's reassembled is quite non-trivial. So the way we do this is as follows. We describe the permission aspect with a separation logic magic wand. So a magic wand you can think of as like a permission-aware version of an implication. And in particular, you have a proof rule similar to modus ponens that says, if you have such a magic wand specification, which basically says, if you give me this part S, then I will give you back the whole data structure. And you have the green triangle, then you can apply the modus ponens rules to obtain the full data structure. Okay, so that's how we get permissions, and we get the value specification. So what will the list contain at the end, with a novel specification construct that we call a pledge. So what does a pledge do? So let me give you a concrete example. So what we do here for this from nth method is we give it two specifications. The second one here is a post condition. The post condition says the length of the result list, so the little green triangle, is the old length of the argument list minus n. So that is, in a sense, describes that the from nth method is not going to mess with the length of the result list or the parameter list, because you get this property. So that's the less interesting part. The more interesting part is the part in the previous specification. This one describes what the data structure will look like once it's whole again. So that's this part here after expiry. So once the borrow of the result has expired, what do we know then? So in a sense, we describe, looking into the future, what will be true when the data structure becomes whole again. And so what we say here is, well, then the length of the parameter list R will be whatever the parameter n was, plus what the length of this green little list is. Now, but this part can be modified by the caller of our function. So we need to say, well, this is not the length that it has when this function terminates. It's the length that it will have whenever the data structure becomes whole again, so that it has right before the borrow expires. So we describe what will be true at the expiry of the borrow in terms of what the caller has done with a part of it. And so putting those two things together really allows a caller to verify interesting properties without revealing any implementation details. And the necessary reasoning support, in particular, the support for magic wands, is available in Viper. And also those parts of the proof are fully automated. So programmers do not have to provide any annotations other than the specifications that you see on the slide. So let me very quickly tell you our experience.
Peter, you only have a few minutes left, so plan carefully.
Thank you, I'm almost done. I would like to tell you very quickly what our results were when we evaluated that to see how well the approach actually works. So we took the 500 most downloaded crates, packages, and added no specifications whatsoever, because we only wanted to evaluate, can we actually synthesize these core proofs automatically? Since our implementation does not support the full language, we filtered out those functions that we cannot handle yet. And we retained almost 12,000 functions, 21% of the overall number of functions, 40,000 lines of code. And when we ran our approach, we were actually able to verify the core proof of 100% of those functions. So that led to the generation of 1 million lines of Viper code. 100,000 of those million lines are annotations that were synthesized automatically. And we also looked at examples where we did provide specifications. So we took a bunch of examples from Rosetta Stone and wrote specifications. And let me just highlight one aspect here. So you see in the upper part here, so those are examples where we only proved the core proof, plus that there are no assertion violations, no panics, and no overflows. And you see that the annotation overhead is very low. So it's typically below 1 line of spec per 1 line of code, which is much lower than you get in typical separation logic proofs, where this number is usually somewhere between 5 and 20. And even if you look at examples for which we did specify functional correctness and verify that, you still get a pretty good ratio, which is much, much lower than what you see in tools for other programming languages. So my point really is that we can really leverage the Rust typesys to make specification and verification dramatically simpler, not only in terms of the amount of overhead, but also in terms of the intellectual complexity, because we can really hide the program logic underneath. So here I gave you the rough overview of what Prusty does. The actual implementation handles much more, like traits and subtyping, generics, external specs for libraries, and we are working on many other features right now. If you're interested, check out the website, and we also have a fairly active Zulip chat with over 50 participants. So if you want to engage in the discussion, feel free to join us there. And with that, I'm done, and I'm happy to take questions if there's still time.
Okay, thanks a lot, Peter. So yeah, let's take some questions. And actually, the Supratik, the second speaker, is also back online. So so you can also ask questions about the second talk if you want. And if it's not obvious from the question, just say which talk it applies to. Let's see. So we have some question in the chat. Jean-Christophe, you want to ask your question?
Yes, sure. If you can hear me.
Yes. Yeah, fine.
Okay, so that was a very nice talk. Thank you. I'm curious whether you can verify data structures with sharing, either immutable data structures with sharing like ropes or binary decision diagrams, or mutable data structures with sharing, like I was thinking about the Morris algorithms for traversing a binary tree in place. Is it something you could do with Prusty?
So there are different aspects to that, right? So if you look at just the safe Rust language, and the safe Rust language does not have sharing in data structures per se, right? So data structures are all tree-shaped. That's also why there's such a nice correspondence with separation logic. What you can have in safe Rust is so-called shared references. So you can have various references into the same data structure temporarily, and those are then read-only references. And Prusty does support those, and we use fractional permissions in order to do that. So here I always gave you like full predicates to describe data structures, but Prusty uses fractions to do the right accounting for shared references, and the fractions allow you to obtain like the full write permission again when all the read-only references go out of scope. So for the actual sharing inside the data structure, which you can obtain via unsafe Rust, we are currently working on extending Prusty in various ways to support unsafe code, but the current version of the tool does not support that yet, but we are working on that actively.
Okay, I think Daniel raised his hand. So Daniel, if you want to ask your question.
Yeah, so this is very cool work. I'm excited to play with it. So I was wondering, first of all, about unsafe code. So how do you handle both the fact that unsafe code can break some of the guarantees of Rust, and also the fact that you can generate things that give the illusion of safety, but for example, you can have reference counted, you can have mutexes, you can have things where the unsafe code is doing things where you do have sharing, but they try to create the illusion of no sharing.
Yeah, these are two very good questions. Thank you very much. So there are two main aspects to that in my eyes. So one aspect is that you would like the reasoning that I described here to remain sound if unsafe code enters the picture. So even if we don't want to verify the unsafe code itself, at least we would like to show that the verification of the safe code remains sound if unsafe code is present in the program. And so, for instance, one case where this would currently not be the case is interior mutability, where you can have side effects, even though you have only a shared reference to a data structure. So we are currently working on that. We are pretty far. We have a detailed design how to actually do that. So this can be done. The second aspect is, how do you reason about the unsafe code itself? And so my take on this is, if you look at the situation where you have completely arbitrary unsafe code, then verifying Rust is as hard as verifying C. And I think this is not what we should aim for. This is not what Rust was made for. I think the philosophy of Rust is that the intention of unsafe code is always to be hidden behind a safe abstraction, right? So you would like to have, in a sense, an interface that behaves like safe code, even though the implementation behind it uses unsafe features. And so our idea for the verification techniques that we're working on is to really use that interface as as like a, yeah, really like an interface where on the one side of the interface, you can reason with the ideas that I've shown you here, pretending that everything is safe because you have this safe abstraction. On the other side of the wall, you actually need to reason about the unsafe code. And we think that we are well equipped for that because that's the beauty of having this core proof, right? We do have a full proof and separation logic for the Rust program. So if we need to go down to the details of pointer manipulation and so on, we can do that because we have the logical foundation. I believe that then we will not be able to preserve this nice abstraction that all the details of the logic are hidden from the programmer. So that's, I think, only possible for the safe fragment of Rust, but at least we will be able to reason about the unsafe fragment as well by using a separation logic that can handle even things like data races and so on.
Thanks.
Okay, thank you. Yeah, I'm going through the chat, and actually I see a question that was for the second talk, so for Supratik. There is a question from Sanjiva Pazal, and he asked whether the technique of for analyzing loops and peeling loops, etc., becomes simpler for Boolean programs or abstractions in general. So can those some of those steps can be calculated if you have the appropriate abstractions, for instance.
So am I audible? Can I?
Yeah, we can hear you.
Okay, great. So I actually lost all the questions in the chat because when I rejoined, it doesn't show me previous things.
No problem. I will fish them out for you.
Yeah. So so was the question from Sanjiva about for Boolean programs or for Boolean abstractions of programs?
Yeah, well, he was asking whether the techniques you presented become simpler if your program is a Boolean program, for instance, or if you can apply abstractions to your source program.
Yeah, so I guess with Boolean abstraction, because you know, you're just reasoning about predicates, but it's not immediately. I mean, it's not immediately the case that abstraction helps in this case, because when we're trying to construct the difference program, we want to make sure that the n-1th version of the program sequentially composed with the difference program gives the same behavior as the original program. So now, if you are talking about abstractions, it is not immediate. I mean, unless your abstraction, you know, does a very, very crossover approximation of the behavior, it's not immediately clear that abstraction is going to help this process.
Okay, I see. All right, let's see. Some people are raising their hands. Tony, are you ready? Go ahead. You need to turn your microphone on. You are still muted.
Like that?
Ah, good, good, perfect. We can hear you.
Good. Question is about deadlock, which is a programming error. Does Rust protect against that?
No, it does not.
Yes.
So that you would have to verify, I mean, essentially by establishing an order on the logs and proving that you acquire the logs in order.
Or use some simple thing like having a special concurrent combinator which only outputs in one direction.
Yeah.
Chaining operator in CSP, but that wouldn't be catered for in your current proof system.
That is correct. Yeah, it's not.
Now, there are other ways of defining incorrectness and correctness in a program, and other design patterns for avoiding the incorrect things, or what they call anti-patterns, which are symptoms of likely places where errors will occur, can be defined and used with benefit in the analysis of programs in the initial model checking of programs. So one would sort of, Rust seems to be very oriented towards separation logic, which is very nice. Rust seems to be very well oriented towards separation logic too, which I didn't know. Sorry, Viper seems to be, so you're sort of building a ladder between Rust and Viper, which already contains the separation logic enforcement that you need. Is that a reasonable summary?
Yeah, that's absolutely correct. Thank you.
Thank you very much. And I would like to, well, no, there are some insoluble problems which I won't bore you with.
Maybe afterwards.
All right, yeah, anytime. Okay, I see Mario. Mario raised his hand.
Yeah.
Are you ready? Yeah, go ahead.
Yeah, thank you. So very quick question to Peter. First of all, thank you very much for your talk. So one of the things that I find most difficult to handle in Viper is the fold and unfold pair, which I guess is also part of the auxiliary annotations that you infer in Prusty. And I guess for that you use some kind of hints from the Rust compiler. But my question is, can you be sure, always be sure that the Rust compiler will give you all the information that you need, so you to be sure that you infer the all necessary information? I mean, you're not going to be missing any fold or unfold here and there. Is there any proof that the Rust compiler will give you all of that?
No, so there's no proof. So let me start with the positive part. So so the proof that we generate is checked by Viper, right? So in a sense, we have various places that would have to fail to produce an incorrect proof. You would have to start out with a type checker that has the wrong information, and then Prusty somehow synthesizes the wrong proof, and then Viper is somehow unsound that it doesn't detect it. And in our experiments that I showed, really ran on tens of thousands of lines of Rust code, and we did not encounter a single example in our language subset. There's still many features of Rust that we don't support, but in our language subset that worked 100%. Nevertheless, there's no proof whatsoever, and it would be great to have a soundness proof for the technique in general. But one problem is that at that point, I'm not aware of even a reasonably complete formal semantics of Rust or a type safety proof of Rust. So in a sense, the foundation for a soundness proof for the verifier are not even there. One would have to lay these foundations first. I hope people, there are papers coming out about attempting to verify or to formalize the Rust language, but many of these attempts are still somewhat partial. I hope that in the not too distant future, we will have a good foundation, and then one could attempt such a proof. But at the moment, this is all validated experimentally.
Okay, yeah. So I guess that's also a nice feature of Rust. It binds well with the Viper verifier, with the separation logic verifier, because I mentioned that for other language it would be very, very tricky to infer these fold and unfold annotations. For instance, I know about your tool for Python, and sometimes I see the fold and unfold that you need to write on the source code. So in that case, it's not so well adapted as Rust to infer those automatically. That is correct, right?
Yes, exactly. Yeah.
Okay. Thank you.
Thank you.
All right. Well, thank you, everyone. So I think it's time to stop. I'm not seeing any new questions coming in.
Okay, so Matthias is one of the key people behind the Ultimate Optimizer. He did his PhD in 2015 with Andreas Podolsky, and his work on Ultimate Optimizer has led to 26 gold medals over 6 years, 26 medals over 6 years, including gold medals at SVComp. So Matthias.
Yeah, okay, thanks for the introduction. In this talk, I would like to present you the algorithm that is underlying this Ultimate Optimizer tool. And so the Ultimate Optimizer is a tool for checking non-reachability, memory safety, termination, and overflow. So several properties, not only safety properties of C programs. And we participate regularly at this SVComp, the software verification competition, and were quite lucky this year that we got some medals. Okay, and I would like to intrigue you with some motivation about the underlying algorithm that says that we have a new paradigm that says that a computer program is just a collection of statements, and the definition of this program consists of two completely different parts. And I think one of the successes of our tool is that we separate these two parts. And so one part is the meaning of statements of this computer program, and the other part is how the statements are arranged. And so the meaning of these statements is defined by the semantics of the programming language. And the way how the statements are arranged in a concrete program is defined by the control flow graph. And so we use two completely different formalisms for this. And so one is SMT, so logic for the meaning of the statements, and we use automata theory for the control flow of a concrete program. Or yeah, let me phrase this differently. We say we have a new view in programs that says a program defines a language over the alphabet of statements. So we say a program has some language, defines some formal language, and the basis for this is some alphabet. And statements, like you see here, some assignment statements or assume statements, are just considered as symbols of an alphabet. Okay, and then the control flow graph, this is an automaton over the alphabet of statements. And since we want to do verification and we check properties, we encode them as error locations, and we say error locations are accepting states of this automaton. Okay, and so here you see the running example that I want to use in this talk. So here given as pseudocode and as a control flow graph, and it's a control flow graph with some special location. This is an error location, and we will consider this as an automaton. Okay, and we will say this is an automaton that defines some language, and the language are sequences of statements, and these are then all sequences of statements that can potentially reach the error location if we completely ignore the semantics of statements. So if we just consider the control flow. Yeah, maybe let's go quickly through this program. So it has two variables, one variable n, you can think of this as an integer variable, and one variable p, you can maybe think of this as a pointer. And at the beginning, we assumed that this pointer is not 0, and then in a while loop, we decrement n, and in the very last iteration, we set p to 0. But at the beginning of each iteration, we check whether p is 0, and we say the program is correct by definition if p is here never 0. Okay, and obviously this is a correct program because the pointer is not 0 at the beginning and set to 0 only in the very last iteration, so it can never be 0 here. Okay, and before I want to show you how we verify this program, I would like to show you some completely other program. So in our formalism, now this here is also a program, and a program with a specification because it has an error location. And now you may wonder whether this is a useful program because, for example, at this location, there's a solve loop labeled by several statements, and it's not clear how pseudocode of this program would look like. And yeah, what I want to say is, well, it doesn't matter, but we need programs like this that look completely useless in our verification algorithm, because we will apply set theoretic operations to programs. Okay, And maybe this is all this was a bit confusing, but let me show you the our approach on an example, and maybe then things will get clearer. So again, we have here our running example, and now our algorithm first checks whether this error location is reachable in a graph theoretic way or in an automata theoretic way. So we can just apply some emptiness check for a finite automaton here, and we will get this word consisting of these three statements of these three letters. And yeah, well, you will see this is not a real counterexample to this program because the program is correct. So as a next step, our approach, well, after it took this sequence of statements, and we call the sequence of statements a trace, we consider now this sequence of statements as a program, because we say every language over this alphabet of statements can be a program. So here's, it's a very simple program where we can give even some pseudocode. And now the next step is to analyze this program. Oh, and yeah, I would like to show you here a small excursus about how we're checking, how we find correctness proofs for straight line codes. And so this is, we use an SMT solver and yeah, encode this somehow as an SMT script and get these, get an annotation. We call it a Floyd-Hoare annotation that is a correctness proof for this program. And here you see a correctness proof given by symbolic execution. This is a proof that will be not very useful for us because it is very, it's very precise. It contains all details that are maybe not important. And in practice, to avoid this, we use something called Greg interpolation. So we like very much SMT solvers that support this interpolation, and then we can get a Floyd-Hoare annotation like this here by using this get interpolance command. Okay, so yeah, first step was we take some trace by just purely automata theoretic algorithms. Then we consider this trace as a program and analyze the correctness of this program. And here in this case, the program was correct, and we have here a Floyd-Hoare annotation that shows correctness of this program. Okay, and now comes the crucial step of our algorithm, or one of the crucial steps. We will next generalize this program. So we have now a correct program, but the next step is to enlarge this program. But we will not change the proof. So we fixed the proof for this program, and now we are going to enlarge this program by adding new statements. And we want to add new statements, or new edges, I should say, in this automaton, labeled with statements. And we want to add only new edges that make still sure that this is a correct program. And we can achieve this by adding only new edges if the corresponding Hoare triple consisting of annotation of the predecessor, statement, and annotation of the successor is a valid Hoare triple. And if we do this, we still have a correct program. And so here in this example, we will now do this for several statements, and we add here some self-loops. And yeah, we can in fact add the self-loop for every statement, but the statement that modifies, that sets P to 0. Okay, and we will do this for all the other locations. And so here it's just coincidence that we add only self-loops. In practice, we may add arbitrary edges as long as the corresponding Hoare triple is valid. Okay, and now what we have is the original program for which we want to analyze whether it's correct or not. And we have a new program that is correct, but now, yeah, this is a complete, or it's a rather completely different program. And now the next step of our algorithm is we consider them now in a purely automata theoretic way. So we are going to check the set theoretic difference of these two programs, because this program defines a set of sequences of statements that can potentially lead to the error location. And this here, it defines a set of traces that are not executable, or that are correct, or that can never reach the error location. Okay, and we check this by using purely automata theoretic methods. And in this example here, the set theoretic difference is not yet empty. So what we can then do is, well, we continue in the same manner again. We take now some trace that is in this set theoretic difference. So it's a trace that can potentially reach the error location, or that can reach the error location in this control flow graph if we ignore the semantics of the statements. And yeah, then let's continue by analyzing this trace again. So we take this trace, we consider this trace as a program, we analyze the correctness of this program, and we generalize this program by adding transitions. And we may add a transition whenever the corresponding triple consisting of predecessor annotation, statement, and successor annotation is a valedor triple. And we may also merge locations if they are annotated by the same statement. Okay, and now we have the original program and two programs that are correct. And we apply again our automata theoretic methods. And in this case, we are lucky. And so we have proven that this program is correct because this inclusion here holds. And yeah, the reason for the correctness is that every sequence of statements that can lead in the error, that can lead to the error location is a sequence of statements that is in one of these correct programs. Okay. Yeah, next I would like to quickly go through our verification algorithm. So we have here this loop. We start with a program, and we have here at the beginning an empty sequence of correct programs, and we check whether the language of the original program is a subset of these languages. Yeah, at the beginning this is empty. Then we pick some error trace. We check whether this error trace is feasible. And if it is feasible, well, then the program is incorrect. But if it is not feasible, well, we generalize the infeasible. We construct a proof for this infeasible trace because we consider this infeasible trace as a standalone program. And then we generalize the program to a larger program and add it to this set here of programs for which we then check whether the traces of the original program are already included here. And if this inclusion holds, then the program is correct. Okay, yeah, then I would like to use the remaining time to talk about interprocedural analysis. So if we want to consider a program with several procedures, then we have the problem that regular languages are not sufficient. Because, well, if we have a regular language, we cannot enforce that this call and return discipline of the specification of this programming language is kept. And so we could have very weird programs like this. And a solution for this is, or could be, that we use context-free languages and push-down automata, but the problem is they are not closed under intersection. So the corresponding class of languages is not closed under intersection. And so we would not be able to apply our algorithm. And so a solution for this was to look at other automata types, and there are these nice visibly pushdown automata implemented by or developed by Alur and Madhusudan. And there we have different kinds of letters in the alphabet. So some letters are call symbols, some are internal symbols, and some are return symbols. And if we use this, we can make sure that this stack discipline is kept. And so then we can implement some recursive program like here we can represent some recursive program like here an implementation of this McCarthy function by such a visibly pushdown automaton. And this visibly pushdown automata have four-array return relations, and these make sure that the stack discipline is kept. Okay, this is one challenge for interprocedural programs. Another is, well, what is the Floyd-Hoare annotation for such a visibly pushdown automaton? And so one option is we could try to proceed with states that also talk about the stack. But the problem is then the locality of this annotation is lost, and it will be very difficult to generalize this program. To generalize a program for which we have a proof. Another option seems to be we use only the local valuation, but this will not work because then the dependency between calls and returns will get lost. And so our solution to this is we compute proofs along traces that we call nested interpolants. And there we have something that we call Hoare quadruples. So for return statements, we need two predecessors. And one is the local state of the caller. And the other is the state or the annotation of the callee before the call. And we can put these two together with the return statement to the annotation that has to hold after the return. Okay. And we can then have Floyd-Hoare annotations for these visibly pushdown automata that are suitable for recursive programs or for interprocedural programs. And we can get rather local proofs that can lead to a generalization of these programs. Okay, I'm not sure how much time is left.
So yeah, I think you have another minute or two.
Okay, then I would like to say that I'm very proud that this approach has also been extended by other people. So there's another extension to interprocedural programs. There have been extensions to concurrent programs, to time systems, and to solving horn clauses, and the approach there uses tree automata. And we ourselves also implemented some extensions, one for checking termination and LTL properties, and there we use Bücher automata, and another one for concurrent systems where we use Petri nets. Yeah, okay, then I would like to thank you for your attention.
Great. Thank you, Matthias. That was very clear, and you did really well on timing as well. So any questions? Feel free to chime in or raise your hand.
Maybe I can
Roderick?
Yeah, so I wanted to ask if you find bugs in your program, whether you can use the same mechanics to find fixes.
We have not yet implemented something there. Maybe maybe some people in Israel, so Batjen Rothenburg, had some ideas on this, but I think she hasn't published them yet. But so I have not done any work on this yet, but I think this is an interesting research direction.
Okay, thanks.
Martin?
Hi, Matthias. Thank you very much for the talk. Very interesting stuff. Possibly unhelpful question. The frame part that you did with the core quad on the return statement, isn't that a separation logic type thing? Isn't that there a star implicitly in there somewhere?
I have not thought about this in this way yet. I'm
not sure if it's a helpful thought. But,
yeah, thanks. I think I have to think about this a bit longer. So there might be some connection between separation logic, but I never considered it as this.
The other one that came to mind, of course, was the interpolant algebra, the language type restrictions on interpolants, because the point is you've got res equals x and x in the caller, and you've got that's a shared term in interpolant sense.
Yes.
Thank you.
Yes, on practice, we compute these interpolants by tree interpolation. But luckily, some SMP solvers support this.
So, Matthias?
Yes.
I have a question. Are you able to reuse proofs from, a library, for instance? I mean, it may be that the traces that you're constructing, you've already seen examples of these elsewhere, and that you could bring in proofs from a library.
Yeah, so you mean I could keep all traces that I found so far that are correct in some database and then check whether they occur again.
Yeah.
Yes, so this is definitely interesting. We have thought a bit about this, but we never implemented this so far. Yes, so if it's really the same library, yeah, then this would probably work. Yeah, in fact, what I had in mind is that you're suggesting that we go from one library to another, because maybe some reasons for infeasibility may be very similar, but variable names are different. And then we would need something like alpha renaming, or I'm not sure if this is the correct term, but the variable x in one library might be a different variable in another library, and there may be a lot of choices how to replace these. Yeah, and I think this is an interesting question, but we have not really started on this yet.
So Ranjit has a follow-up, and then I'll go to Supratik. So Ranjit first.
Just following up on, my video is off. Can you, I guess, is there some way you can save the, what did you call them, the pushdown automata that you get for some function? Let's say you have the function foo that's used in 25 different programs, and somehow I've analyzed it once. Can I save the pushdown automata for foo and reuse it across different clients? I think.
Yes, definitely. So this is possible. I should have said, we already did some work there where we really used the very same library or the very same automaton or the very same summary. And yeah, this can be done. And in some cases, it saves a lot of time if the summary works again for a different specification. But we also had cases where it was just a waste of time because the summaries did not work, and to look up all these summaries costed more time than it saved.
So you mean the problem was the summaries didn't really generalize across, they weren't general enough to be applicable across the different clients?
Yeah, it depends from program to program. So in some cases, they were general enough and sometimes not. And yeah, I think that's it. So we got some speed up, but I think, yeah, maybe we should, we have to try it on larger programs. So yeah, I think it would be especially interesting to verify a software project over time. So where you have new commits every day or so. And then I think it's possible to reuse a lot of this old information. But we have not tried this yet on a larger software project.
Supratik?
Yeah, hi Matthias, very nice talk. So I want to ask that when, in this slide that you're showing right now, when you have nested interpolants, so is there a specific kind of logic that you use for this? For example, if I'm reasoning about, programs manipulating dynamically allocated memory, I mean, would you need separation logic, interpolants and separation logic? I mean, is there a specific logic that you use for these nested interpolants? Because it does look like that, different logics allow you to maybe specify things that are relevant that you want to say.
Yes, so in practice, we use SMT theories of dissolvers that can provide interpolants. Or well, we have some techniques where we can get something similar as these crack interpolants by using unsatisfiable cores and symbolic execution. But so the theories that we use are, for example, the combination of bit vectors, floating point arithmetic, and arrays, or integer arithmetic and arrays.
But is that sufficient? I mean, I guess, I don't think we have things like separating conjunction or the magic wand in SMT theory.
Yeah, so we do not use separation logic.
Okay.
So maybe this would be a good idea for the future, but at the moment we do not use it. Maybe we use something very similar, and you could view all this as separation logic. But I'm not familiar enough with separation logic to definitely say that this is just another form of separation logic.
Okay, thank you.
Okay, thanks again, Matthias. So I enjoyed the talk, and we'll switch to the next talk.
Yeah, thank you.
So I believe I need to pause the recording. So is that right, Roderick? I need to pause the recording?
I'm fine either way, Shankar. So I didn't sign the right form, I think. Whatever you want.
But can you sign the form later on, you think?
So I don't know like what the copyright is and all of the pictures, etc. That's the problem.
Okay, so let me pause it then. I think we'll just play it safe. Okay, I've resumed recording, everyone. Yeah, hey, Marika is known for her work on program verification, specification, and software reliability. She leads a group at the University of Twente on formal methods and tools. So she has been working on this particular project actually from an ERC grant starting in 2011 for the verification of concurrent software. And so she's actually received the Netherlands Prize for ICT Research in 2013. And so she'll be telling us today about workhorse.
Yes.
Sounds a bit like workhorse. So.
Yeah. So Vercors is actually a mountain region in France, close to Grenoble. So the picture that we use as logo for the Vercors tool is from that region. So you can see the area is beautiful. I think our work is beautiful as well. So I'm going to talk about the Vercors tool indeed. So a program verifier for concurrent software. And so usually I start my talks by talking about, so software is everywhere. And as we all know, all software has errors, and all these software failures can have enormous impact. Just today, somebody from my faculty sent a message about that yesterday. A lot of internet sites were down because of some small software bug. So it's really important to do things to make your software reliable. And with our work, we're looking in particular at a concurrent and parallel software where you have these multiple threads of execution, which make it even more difficult to predict what are all the possible behaviors of my program. And so how can I guarantee that in all situations the software will work well? So the Vercors philosophy is actually that in the end, software verification should be everywhere. Now, this is a very ambitious goal, and I always say it's very good that I still have many years until retirement, but this is really what I strive towards when developing the Vercors tool. And I want to make a tool that is usable by other people, by software developers, and that they in the end ultimately can really integrate in their software development process, but there's still a long way to go. So what I originally planned to do in this talk is first tell you a little bit more about the Vercors architecture and the Vercors specification language, which is based on permission-based separation logic. So for those of you that have seen the talk by Peter Müller earlier today, you will recognize some of the things that he mentioned. You will also see, because we are not reasoning about Rust programs, but about other languages, that we still do need quite a lot of annotation. So that's also something we're looking at. And we're studying how we could reduce that, because I think in the end, if we want to make these techniques usable for software developers, we have to make sure that we reduce the number of annotations that people have to write and the effort that is needed to verify programs. So after the general discussion of Vercors, my original plan was to dive into 3 recent case studies, but I realized when preparing this talk that I wouldn't have the time to do that. So today I will talk about our case study on parallel nested depth-first search, where we verified a parallel model checking algorithm. And I don't have time to talk about parallel prefix sum or the applications of it, so I'm not going to discuss that. But if you would like to know more, I'm very happy to tell you more about this offline, of course. But so I wanted to start with the Vercors architecture. And actually, so Vercors itself, the Vercors verifier is a tool that can take input programs as input in different programming languages, and then we transform it, and there we rely on Viper, which is one of the tools that is developed in Peter's group. I realize now it says developed at ETH Zurich. Of course, Alexander Summers also contributed to it, so it's now also developed in Vancouver. But so what we do is, on top of Viper, which is this intermediate verification language that can understand these permission-based style specifications, we built a tool that can understand programs written in high-level programming languages. So we started out with Java, but we're now also looking more and more at C-like programs. So in particular, we're working on having support for OpenCL, which is a programming language for GPU kernels. We've also been looking at OpenMP, where you write sequential programs with compiler directives about how to parallelize the program. And all these programs are then transformed into Viper input in such a way that if the Viper program is verified, then we know that the original program with its annotations was correct. On the slide, there is also PVL, which is our own prototype verification language. The examples I will show to you are actually in PVL. PVL sort of has all the features of all the languages we want to support. And it's the richest and best supported one. Of course, to actually develop such a tool for a real programming language, a big challenge is also to make it work for all the features of a language. And that's a task where we still have to make some progress on. So that's the idea. And then, as I said, so our specification language, the assertions are written in permission-based separation logic. So where before in the talk by Peter, he showed you the points to permission, we actually have a variant of that, namely a permission annotation. So a permission annotation for a variable, it says that a thread has a certain permission to access a field on the heap. And this permission can then be a read or a write permission. On the next slide, I'll say a bit more about these permissions. But what is important is then that all the formulas that we state about heap variables, they should be properly framed. So you can only reason about heap locations that you have access to. And this is then checked by the tool when we write our specifications. And then we have the separating conjunction, the star operator, which helps us to support the local reasoning. So it allows us to say this part can be verified in isolation. In fact, what is not on the slide, we also have support for magic wands, and then we have features support to write predicate specifications and so on. So we really capture all of permission-based separation logic. So as I said, I wanted to say a bit more about these permissions. So permissions to access a certain heap location, they can be write or read permissions. And we encode this by a fractional value. When a thread has a permission 1, that means it has a write permission and that it has exclusive access. A read permission is any fractional value between 0 and 1. Now for the program logic that is implemented in the tool that is supported by the tool, there is a global invariant property proven that states that for every heap location, the sum of all the permissions in the system is never more than 1. And that means that if we can verify a program with our program logic, it is guaranteed to be free of data races. Because if a thread has write permission to a certain location, no other thread can have access to that location at the same time. If a thread has read permission to a certain location, any other thread that has access permission to that location also can only have a read permission, so it cannot suddenly change that location. And then of course, read and write permissions can be exchanged, so it's not static. Whenever threads synchronize with each other, permissions can be exchanged. And if a thread at some point has 2 half read permissions, it can combine that into a single write permission. And then, as I said before, permission specifications frame the functional properties that we specify. So what I wanted to do now is to show you a few small examples to give you a feeling for what it looks like to specificate the program specifications in Vercor. So these are all very basic examples. This is the first count example where we have an increment operation. And what is interesting here are the permission specifications. So the precondition says that this function or this method requires a write permission to the field count. And then it states that it will only give back a read permission. So it actually loses permission somewhere inside. And as a consequence, if we have a method like the increment 2, that is at the bottom of the slide, which calls the increment function twice, then the second call to this increment function will not verify, because the precondition of that function requires a write permission, but the permission has been lost. If we would change the specification of the increment function so it would return a write permission, then of course this example would verify. And so notice that here we also add the functional specifications. So of course this is a very simple example. Now this is again a simple example. This is a function that goes through all the elements of an array and puts them all to 0. And of course, if you want to do that, you need to have permission to access all the elements in the array, and you need to know that the reference to the array is not null. And then we have to write loop invariants and things like that. There's one important thing here. We use a keyword context everywhere. This is an abbreviation that we use for a specification that is both a precondition and a postcondition and can be added to the loop invariant. So this is simply a way to reduce the number of specifications that we have to write. But otherwise, this should look all quite straightforward to you, I hope. But then on the next slide, I have a parallel block. So that is where the concurrency enters. So here in this parallel block, so in PVL, we have just added a parallel block to the language. And this is stating that in the clearPar function, there will be threads created from 0 to the length of the array. And every thread will put one element of the array to 0. So you see that the function specification is the same, except that the context everywhere for the permissions is changed to a context, because now inside the function body, the permissions are separated. So we create a.length threads, and each thread gets only a permission to write to that single location of the array. And these parallel blocks that we use here, this is the basic construct that you use, for example, to write GPU kernels. So when we reason about OpenCL programs, in essence, they are just encoded into these parallel blocks. Of course, with this parallel block that I showed you before, all threads were doing things on their own memory location, but of course you also want to have shared memory sometimes. So you can do that with a lock, or you can protect the shared data by an atomic operation. So in this example, I extended, I added a field sum, which is protected by a lock. And then I used the parallel block again. But inside the parallel block, each thread will add its own value of the array to the shared variable sum. So that is why you need a lock operation before you can actually execute the code inside the body of the parallel block. What we do then is we add what we call a resource invariant, a specification that states when a thread acquires the lock, what permissions does it obtain? So the lock invariant that is specified here states that a thread that holds the lock gets a write permission on the sum field. And so for every thread, we just specify that it has a read permission on its own element of the array. Then it will acquire the lock, so it will obtain write permission on the sum field. It will update the sum field, and then when it unlocks, it will release the permission on the sum field again. So that was a very basic, very fast introduction to how to write some specifications within Vercor. So now what we've done, of course, this is all very basic, but we are looking, at the moment, we're working on doing a lot of case studies on verifying various parallel algorithms. So we've verified the prefix sum algorithms, we've verified parallel algorithms that use this. We also have a verification of a parallel single source shortest path algorithm. And in the rest of this talk, I'm going to focus on one particular case study, which is a parallel nested depth first search. And this is a case study that was published at TACAS 2020. It was done together with Wietse Ortwijn, Jacob van der Pol, and Sebastian Joosten. So this parallel nested depth first search, it's a model checking algorithm. The original sequential version for the nested depth first search was verified by Jacob van der Pol in Daphne. And so my PhD student, Wietse Ortwijn, for a long time during his PhD, he said, yes, I want to verify that. And then I think in his fourth year, at some point, he came to the office and said, yes, now I'm able to verify it. So what is interesting about this case, about this algorithm is, so it's implemented in LTS-min. It's an algorithm that goes through a directed graph, and it looks for a cycle, accepting cycle. So a cycle that contains an accepting state. And because reachability of such an accepting cycle can be used to encode LTL properties. So this is then a parallel algorithm to do model checking of LTL properties. And so they developed this in LTS-min. They had a pen and paper proof, but we actually mechanized this in Vercor. And we first verified a swarmed version where all the threads do their own independent parallel processing. But what is more interesting is that we also verified the parallel version where there was actually shared state. To be able to do that, we had to rephrase the proof to make it actually suitable for mechanism. So you really need to provide certain proofs as an inductive argument so that you can phrase proper loop invariants. But once we had it in the paper, there were also some optimizations proposed, of further optimizations of the algorithms proposed. And once we had this, we could very easily also prove that also these optimizations were correct, well, except for the one that was buggy. So here's the pseudocode of the sequential nested depth first search. I don't want to go through that, but I want to show on an example very quickly how this works. So the idea of the algorithm is that you have, well, you have two depth first searches. First, you go through the system, and then at some point when you reach an accepting state, you will start a special search to see if there's a cycle. So the idea is as follows. When you start exploring states, you color them in some cyan way. You go through all the reachable states. Now in state 4, there are no outgoing edges anymore. So this state is fully explored and it turns blue. And you do backtracking. But then when you get to state 2, there's still an outgoing edge. So you start a new search via edge 2, node 1 to 6, and then to 5. Now in 5, again, there are no outgoing edges to states that have not been visited before. So you backtrack. And now when you get to state 6, because it's an accepting state, you start a new search, the red search, to see if you're actually on a cycle. And what happens then is that you color your state pink in addition to being cyan, and you start searching again. So we go to 5. Now you could see 4 is also a next reachable state. It has been explored. So this will continue and all the pink states will turn red. But then from 5, you can go to the state 1, which is cyan. So it means that it's not fully explored yet. And that indicates that there is actually a cycle. So that is how the sequential algorithm works. And what you can prove then is soundness, is that all cycles that are reported by the red search are indeed accepting cycles, and that if there exists an accepting cycle, it will be reported. And so this is the property that Jacob van der Pol then proved using Daphne for the sequential version. And so we transformed that into a proof for Vercor, so which meant that we had to add all the permission annotations and so on. But after that, we first proved the swarmed version, so where all the threads execute all in parallel, but they all keep their own local state. So there is no shared state, so they really process completely independently. So that was very straightforward to prove. But the disadvantage of that algorithm is that the parallel threads do not profit from the work done by the others. So then the parallel version of this algorithm, you make the red colorings shared among all the threads. And then that means that if you at some point reach a red state, you don't have to continue exploring anymore, both in the blue search and in the red search. I don't have the time to really explain all the details, but I hope the overall idea is clear. So here, again, I have some animations. So here, first thread 1 would start searching. It would at some point say, oh, from state 6, from node 6, I cannot continue anymore. So then it would backtrack. It would reach the state 1, which is an accepting state. So it would start a red search from there. It would go the same way again. And then it would say, oh, from state 6, I cannot continue. So I actually, from pink, I turn this red. And now the point is that if in parallel, thread T2 is also doing a search, then it can see that node 6 was already colored red. So when it will do its own search and maybe go via node 3, then it will say, okay, from there, I can only reach a state that is already visited. So I'm an accepting state. I start a red search and I see already a red state. And that allows me to immediately turn red, and I don't have to continue the search anymore. So this makes the whole process more efficient. So here is the algorithm where red...
America, about 2 minutes.
Yeah. Yes, I'm almost done. So where red is the shared variable. And now the interesting thing is, so how did we mechanize this in, what were the challenges in mechanizing this algorithm in Vercor? And I fortunately decided to skip all the details from my slides, but so first of all, it's the graph representation. So if you would really represent a graph with pointers, it would be very challenging for the verifier because you have to deal with all the pointers. So we had to choose a suitable representation using arrays. And then we had to mechanize the correctness proof. So as I said, we had to handle the permissions also for the shared state. And we had to rephrase some of the proofs using an inductive argument. And we used quite a lot of auxiliary ghost variables to keep track of the state of the algorithm. So that was the way in which we managed to actually do this proof. So that was one case study we did in Vercor. So there's a lot of work going on. I have quite a large group of people working on Vercor. So we're looking in particular, well, so Vercor can reason about different concurrency paradigms. It can reason about different synchronization techniques. We're also looking at reasoning about more advanced functional properties by means of abstraction, where we can show that the program behaves as a certain abstract model. And as I explained to you, we can reason about different programming languages. We're working at the moment very much on annotation generation, because one of the big drawbacks of this approach is that you need to write lots and lots of annotations, and a lot of these annotations feel like boilerplate annotations. Another thing we're working on at the moment, which I think is also very interesting, is looking at program transformations, where you have a verified program and then you optimize it to improve the performance, but together with the program transformation, you also transform the specifications so that you can prove that the resulting program is still correct. And we're looking at this in particular in the context of OpenCL kernels, where performance is really an issue. And we're doing more and more large case studies. And to conclude, if you would like to try out the tool, you can try it out online. You can also find more information here. And I think I should say a big thanks to all the people in my team who helped me realizing this. So that's all I wanted to say.
Thanks, Marika. That's really a lovely talk. And so let's see, I have a couple of questions and then we can ask the others. So where is the annotation burden actually most prominent? Is it in the permissions or is it actually in the kind of semantic invariants?
It's the permissions are one big thing. The other thing is that you need to add things like array bound. So I think that there's a lot that have to do with actually proving memory and thread safety. So the permissions help you to prove the thread safety, but also array accesses, proving that all the array accesses are always within bounds, that things are non-null. Also, all these kind of things. They give you a lot of annotations and nobody wants to write them. They're uninteresting. The other thing that was also mentioned in Peter's talk is then the unfolding and folding of predicates that you have to. So there we've done some things. So you abstract something in a predicate, you open it up to reason about it and you close it. We've done some things in the tool to at least in some cases do this automatically, but it's steering the verifier.
So do you run into any situations where you need to actually, be a little more explicit with kind of rely guarantee conditions on the thread interference?
No, I don't recall now that we ran into that.
So do you, for example, do you have situations where, as long as a thread is incrementing a value, it's not going to interfere with a property, for instance?
Yeah.
I mean, like if you're counting in
yeah,
you can always count in parallel.
Yeah, I don't recall that, but there might. Yeah, well, if you do things like counting in parallel, that's where we would need it. But we've also, so one of the focus points is that we try to look at case studies of, so I think it's too early to give our tools to industrials, but we try to get industrial case studies or then we get a lot of code and we try to extract something that is interesting from them. And what I see in practice is that the way people use concurrency is often relatively simple because they want to keep things simple so that it's not such nasty things often. That's what we, and for example, if you look at the OpenCL, the GPU programs, the kind of concurrency you have there is quite simple. It's just that you have to guarantee that there are no data races.
Okay, Martin has a question.
Hi, thanks for the really nice talk. Could you use your permission model to do semaphores? Because it's a sort of counting type thing.
Yeah, we could. Well, that's a bold statement. We have been specifying semaphores. Now the good question is, did we actually, so we could verify the implementation of a semaphore and yeah, we did. And I think we've then also developed examples where we used them.
Cool, thanks.
So proofs that you're doing, are they, parametric in the number of threads, for instance?
Yes. Yeah, that's the yes, they are, well, they are about normally the number of threads is not specified, so it could be any number of threads. When we're looking at, so I mentioned we try to do abstraction-based modeling. So we try to, for example, we're working on a leader election protocol, and then we say that the code itself behaves according to an abstract model, and then we want to check basically the leader election property using a model checker. And there we run into the thing that the model checker itself, it cannot be an unbounded number of threads. So that's something, well, we hope to look into at some point we have some vague ideas how we could solve that. We talked with Jan Frieso-Grote and he just said, well, if you can verify it for 7 processes, then it works for anything. So he was not, that was his opinion.
I mean, there are actual theorems like that. I think that's true of dining philosophers, for instance.
Yeah.
Peter?
Yeah, thank you very much for a very nice talk. I was wondering, does VSOW04 have support for RACI concurrency, or do you only look at data race free programs?
At the moment, we only look at data race free programs. We have some ongoing project to maybe look at some benign data races, but otherwise we look only at race free programs.
Okay, thank you.
So Martin, did you have another question? Martin, your hand's raised.
Competition question.
No, sorry, I'm just struggling with the user interface. My bad.
Okay. Okay. Any other questions for Marike? So with that, I'll thank all of the speakers in both sessions today. I really enjoyed the whole day a whole lot. So thanks a lot, and I'll pause the recording and